Hello, everybody. How's it going? So we're going to have a nice presentation today about automating your ML process and actually being able to considerably speed up the whole pipeline. So the way I had this at least conceptualized is it's a bit more of an intermediate level workshop. In fact, we're probably going to be focusing more on covering the overall like thought process and application behind setting up automated pipelines, and also go into a bit more of the not necessarily the technical specifics, but the general overview about uh, the overall, I guess you could say, philosophy of using automated machine learning to basically build out and create products in a way that's very sustainable and rapid. So let's get started. If you have any questions, just ask them in the question box. I'll try and answer those as needed. But I have one question here first, which is, what's the goal of doing this? And the main goal that we're trying to help achieve or help that we would want to have as part of our own AI like operations is to be able to like modularize model creation, assessment, validation, and optimization. And this is something that will, and the reason we want to do this is for speed and efficiency, as well as to help discretize the search space that you're looking into. So let's step a little bit back. So the problem here is that when you're creating an AI model, you need to first understand both what the underlying problem is, as well as be able to determine specifically how much of that problem you're going to need to explore in order to be able to produce a solution that can achieve the kind of results that you want to find, right? And a lot of this is something that's done in the typical process of you would have your own like Jupyter notebook or something set up, and to do this in the very like I guess you could say more amateur or less production focused way would be to go through, assemble your data set, start doing the like general statistical techniques to determine whether or not that data is qualifiable for the use case that you want to pursue. Then you would manually go through and start iterating on each model training and basically build out your entire process. And after you do that, a lot of this is just doing iterations, making some adjustments to some of the parameters. Oh, maybe I can get better accuracy if I change some of the features, or like if I get some additional data, or if I do some additional feature engineering to like do some dimensionality reduction on some of my inputs. And by doing that, you're eliminating certain avenues in the underlying domain. And this is something that does not necessarily have to be exclusively an iterative process. And in fact, you could take advantage of the fact that there's a lot of like tools and services out there that help you parallelize these operations in order to do multiple experiments simultaneously, and thus allow you to explore more of the search space without necessarily increasing the amount of effort that you would need to put in uh, to do that operation, or at least exponentially increase the amount of work that results that you get out for any specific unit. So it's just more efficient to get this set up. So in order to do that, we need to modularize each of the components and then go through and build out a dedicated ML pipeline that can take data directly from the source location and then convert it into something that's very reasonable or very usable direct models as an output. So how do you get that set up? I'm just going to skip these actually. So let's just, when in this process do you need to get started, and how would you actually get set up with an AI pipeline here? So essentially, each of the projects, or like the general AI project, is split up into these four main phases. So the first phase is the data aggregation, the problem space exploration. So I was mentioning earlier, essentially what we're trying to do in this phase here is to go through and build out and determine what the suitability of the data is for determining some target output. So there's really a step 0 before all of this, which is to identify specifically what your business goal or the goal of what you're trying to set up is. The second step is to find data that is statistically relevant or specifically usable for that type of goal, and then be able to identify essentially what specifically needs to be done with that data in order to produce a meaningful output. And what you're doing in this phase is a lot of cleaning up data, identifying new data sources, and looking at varying graphs and doing basic statistics. So it's not something that's very suitable for setting up to be very automated, because a lot of it is new and experimental thing that you're trying out. However, that doesn't mean that it's not that doesn't mean it's not something that you would need to have in your ML pipeline. What it means is that it's something that you need to set up and build out, and you need to do it in a way that is mindful of the fact that you are going to be using it as part of your rest of your ML process entirely. So when you're doing model selection, which would be the next step here, and I actually set this up as this may not be exactly what you would consider model selection, but I include basically the whole feature engineering and selection process in here as well. And this is all because what we're trying to do is just identify both a methodology and the underlying parameters that are required for creating a model that's capable of or a skillful learner for that particular type of problem. And when you're going through this problem space, what you'll need to be doing is being very iterative in this approach. If you have already selected a technique, then you're selecting for parameters. And if you've not selected a technique or parameters, then you need to do both. And all of these are very not rote per se, but they're very set tasks that need to be sort of accomplished. And because they're set tasks, you can easily create different components for doing these experiments, as well as, since you are going to be using similar validation metrics across all of your different model categories, you'll be able to determine essentially how valid your current techniques are when it comes to creating one of these strong learners. And in order to do that, there's quite a few different auto ML tools. And a lot of this is actually considered as part of the ML ops process overall, if you want to look up a new buzzword. But basically what we're doing there, or what you would need to be doing there, is setting up an apparatus or using an existing framework that can allow you to build out and try different techniques and different pre-processing for features, and then compare their performance across multiple different validation sets. That way you can get a better understanding about whether or not what you're doing is impacting the true mean, or whether or not you're getting closer to producing that strong learning. So this is something that's very automatable, because a lot of it is just trying out the same technique with different input features. So as long as you are mindful in the previous step about how you're setting up the data and you route it to specific places, then what you can do in this step is create individual building blocks to do each feature engineering step, chain them together in a way that allows you to dynamically create different data, different input data sets, and then feed in that into each type of model that you are trying out, and validate essentially your technique across that model, and also across the entire space for that methodology. So doing this will drastically improves the amount of ground you can cover. And because it does that, you can get a better understanding about both what the problem space looks like, as well as being able to directly see a more pertinent improvement immediately, as well as the fact that because this is something that can be very easily parallelize, especially if you have already outlined exactly what you need to have done. You can, within a very short amount of time, easily do this coverage and get a set of reports that you can immediately work on for your next step. And then as soon as you've selected your model, then comes the optimization. So when you have your final model and you then need to start training it against your whole data set, as well as getting it set up for like exploiting the maximum amount of, of potential out of that model. This is like also a very easily automatable process. And in here, basically what you would be doing is you're going to be messing with the hyperparameters and then retraining the model with different sets to determine what the relative performance will be across the entire data set as provided. And this is kind of also a machine learning problem in and of itself. In this case, it's more, I guess you could say, generalized to every type of machine learning model to some degree. In the further examples, I'll probably be focusing a bit more on talking about predictive type or classification type models, as opposed to something that is more exploratory in terms of segmenting things out, like class of like a SVM or an LDA type model, where you're doing more recognition of or extrapolation of existing data into specific categories. So regardless, with any of these sorts of models, what you're essentially doing is you're training or exploring a different domain on top of this. So in this case, it's the model registry domain when it comes to determining what parameters for the model itself determine its learning capabilities. And this is typically a much harder task than getting the raw data and then going through and producing an output. Because at least in that segment, there are some assumptions you can make about the continuity of the underlying data set and the model itself, which helps determine essentially what is going to be built out and how you're going to be building that out in a way that would be effective. Uh, so because you can't have that same level of determination on the hyperparameter tuning space, because the model itself is something that does not necessarily discretely link the input features to the output features. Depending on the type of model you use, it could be very, I guess you could say, difficult to directly relate this. And the risk that comes along with this is that you are very capable of missing these spots. So for this, you're capable of also improve. So this is just basically at that point, it's a numbers game, because you can't directly correlate specific hyperparameter changes. So it's not a solved, it's not an analytically potential, an analytically solvable solution, simply because of how it's set up. So this is also something that you can automate simply because it is basically a numerical game here, where you're trying to go and cover as much ground as well as like analyze specific components and build them out directly. So in addition to that, the next step here is also like the monitoring and maintenance of varying models. And what we're doing there, or what we would need to have set up for that, is to just ensure that the model that we've created actually works and achieves the goal in a real life environment. So with the training that we have set up, that is also something that is not directly correlated to what we're predicting. I mean, it is, but because the predictions that we produce are going to be affecting people's or maybe affecting people's behavior, or are going to be used as part of a prediction system, as that model gets used, and especially for certain use cases, like let's say if you're making a recommendation engine for like a like product site or something, that affects what the input data will end up looking like, because you are now interfacing with the data itself with your predictions, and therefore you're creating additional problems that are going to be occurring within that data. And then because of that, it becomes something that needs to be more directly like monitored on a regular basis. And this is also something that can benefit from doing in an automated way. So as part of this, your main goal for monitoring and maintenance is to basically check and collect different data about how your model is performing, what kinds of inferences you're producing, as well as how those inferences or how that's affecting the determined or the specified outputs. And as you're tracking those metrics, you need to then look at whether or not the model is still performing to an adequate degree to meet the fundamental goals that you're trying to set up. And for this, it's also a majority of like analysis of the incoming data and then doing retraining based off of that data if it is required. If it's not required, just keeping tabs on all of it. So when you're building out your AI pipeline or your ML pipeline, what you want to do is discretize each one of these into specific components, and then build them out in such a way that you can reuse different bits in subsequent steps. So let's just get started with automating model selection here. So essentially what we're doing on that front is we're going to be, we're going to need to lay out some things here in front, which is basically the ability for you to automate this process is highly dependent on the degree of experimentality that you're going to be implementing within your technique or your team's technique. This is heavily correlated to exactly how much of the problem that you are aware of before and how much intuition you want to apply before implementing a certain technique. So depending on your team and the problem that you're dealing with, this is something that can vary very substantially. In particular, so to give like a quick example here, basically, if you know you're going to be producing something like a chatbot or something along that line, it's a sequence-to-sequence type model that you're going to need to be creating. So if what you're doing is something like that, where the space is fairly well trod ground, then if you intend to use something like a pre-existing model and then do transfer learning from there, you're basically implying a certain amount of intuition on that front, at which point, because you've already limited the search space by doing that, you can very easily produce multiple different like views on the same technique, and then be able to easily like set up an automation pipeline for it, because you've already eliminated like one entire parameter, which is the technique used, and that's a very large parameter. So you've basically cleared out a large portion of the search space already, which leaves just doing the more iterative work of selecting between the different input features and like determining whether or not you need to make adjustments on that front. And that's something that can be done again, like in a very clear and standardized way. Secondarily, data management is something that's going to be absolutely essential for how you get this set up. Primarily what it does is you are going to need to keep track of all the input data that you're going to be feeding in, both from external sources and from internal sources, as well as going through and setting it up in such a way that you can easily reuse and manage this data across the multiple different steps of your pipeline. So to give another sort of example for this, basically, for a particular application, let's go back to that like recommendation engine. You will need to do, when you get the input data, you should, it's going to be potentially in like one large database that you will then be pulling from for all of your subsequent steps. But really, what's important to keep track of is that every time you add an additional step, you need to also feed it back in and be able to directly interface with specific outputs for specific steps, so that you can draw upon different components and then reuse them in a way that will allow you to basically uh, build out a whole set of pipelines. And typically, what's being used for this is like there's varying techniques to get this set up, and we'll cover them in a little bit actually. So the other thing is that your ability to convert your existing like AI, I guess you could say, your existing methodology is how modular and independent your code is already. And by independent, I mean independent of other parameters within the same sort of code base. And by modular, I mean easy to just reuse and separate out into separate instanceable, runnable, or instanceable functions that can be then called upon for producing the rest of your application. So typically, what most people do when hacking on a Jupyter notebook and getting their whole thing started is to just build out the whole pipeline, then go back through and make some adjustments to how they're calling different methods or building things out within that pipeline, within that notebook, and setting it up in a very like straightforward way based off of what they are currently interested in looking at, what outputs they want to see, and what they're doing in terms of like modifying the features. And because of how that's set up, it actually doesn't lend itself very well to implementing as part of an ML pipeline unless you keep in mind that that is something that you are going to want to have set up in the future. So a lot of it's changing the mindset of exactly what you need to do uh, when developing an AI model or any sort of machine learning technique is to keep in mind that whenever you write something that's going to be modifying the data, even if you don't necessarily intend on using it to to use in your current technique, you should still try and discretize them as individual functions that can just take in the input feature or the input data, either the raw data or the outputs of another like set of functions, and then basically build out a sequence of these and then basically build out each part as an independent piece. Uh, by doing that, you can then have it lend itself very easily when you want to transition from doing things in a more like linear approach to doing things in this more automated way without having to go through and do a lot of additional refactoring. So if there's any takeaway that you take from this workshop, it's to try and focus on making a bit more repeatable when it comes to uh, creating different functions and components within your code base. And even if you're working in a Jupyter notebook, it's probably a good idea to like think about this in a way that you're creating something that is potentially going to be used as an extra step in your ML pipeline. And being able to think about it in that way requires you to understand to some degree what you're going to be doing and in which order. And try not to overload any particular step with too much effort. Otherwise, it'll be very difficult to like expand that out to the rest of your pipeline in a way that's going to be performant. All right, so let's just do a quick review of some of the tools and techniques then. So I mentioned this a bit earlier, but there's quite a few different like application sources that you can use to get this sort of thing set up. And basically what you're doing there is you're going to have three main like categories of technique, at least in terms of how much use case you'll be setting up directly. And for that, basically what you'll be doing is you'll need to go through and build out the overall like setup for your pipeline, as well as building out each one of the additional components in a way that's going to be good. So primarily we have the out of the box type techniques, which are going to be your AWS SageMaker or your Azure ML pipelines or GCP. Or there's even a couple of other like independent companies that are now doing AutoML as a service. And these things will typically handle everything from data management to also provisioning additional resources. I'm not going to go into them too much, but basically what we're doing there is for each one of those, they do have their own independent methodology for how to set up jobs or different tasks within your pipeline. And they are a little bit different, but they're also very similar. Essentially, uh, all of them still fundamentally relate to that concept earlier about making sure that each one of your components are modular. But for example, in SageMaker, you would be setting up different lambdas or other operations within AWS to call in sequence to then run independent operations from each one of your like notebooks. And then using that data that's then going to be stored in an S3 bucket and then loaded into a notebook, you can then do the inference and training of the model itself. And in fact, they also have out-of-the-box models you can use to do everything from like regression, classification to more complex like neural network training as well, or doing things that are more heavily related to like NLP or very specific techniques. So the downside of using one of these is definitely that you are going to be kind of limited in the types of things that you can get set up because they do have very specific procedures and how things need to be set up, how your data needs to be handled throughout their system, and you'll very quickly become embedded with all of their utilities because you'll need to get them set up in a way that is operational for them. Uh, so Azure's ML pipelines works in a very similar way. They have an SDK that you can basically call either from your own machine or something that's provisioned on their platform. And from that, you can basically set up your data pipe, set up your data sources, load them into different locations within Azure's like cloud storage system, load from those store locations and run specific tasks like any of your feature engineering by just calling those functions within individual operations. And then from there, you can pass them out into additional processes to basically build out your whole pipeline. GCP offers another option as well, and this is with something that they call Kubeflow, which does take advantage of the fact that you may already be working in a Jupyter notebook and basically allows you to separate out individual cells of that notebook into each step of your data pipeline and then run those cells in a way that you can basically scale it out across multiple different data sources. So this is part of being a little bit aware about how you are going to be implementing your ML pipeline when you're creating or when you're doing the earlier steps and hiking away. This is because you may have the opportunity, or you may be, if you're going to be using something like GCP, you may actually be concurrently creating something that you can convert into your ML pipeline without having to do too much additional work when it comes to getting things set up, provided you keep in mind that you're going to be needing to have it set up in a certain way to make it extensible to that front. So the next like level down are the like auto ML frameworks. Most of these do the following. So I gave you a short list here of a couple of Python/R related like auto ML frameworks. For the most part, these will be primarily Python focused simply because Python does lend itself a lot better to being modularized simply because it is uh, generally used, at least outside of the data science space, as like an automation utility like that. And because it can be set up in like that sort of same application way, it makes it a lot more straightforward to build out the model in that using that language simply because of how it's organized. But there's actually like dozens of these. There's a whole bunch, and depending on what your use case is, some may be better than others. I've listed some of the more popular ones here, and basically the pros and cons of these they share some of the same like limitations as the more out of the box solutions. However, they are a lot more extensible, especially if they are in Python, simply because you can also go through and make modifications to how they're running, or make your own like additions to the process in case you want to be able to support different techniques that they may not have inbuilt support for, without having to like start from scratch, which is definitely not something that is advisable necessarily. So these sorts of tools usually require like additional data management utilities as well. So they typically stop or they typically start right after the data is being passed in, and they will then proceed to do a lot of the optimization steps, or a lot of the search area like exploration automatically. So for example, we'll go into setting up Teapot a little bit later in like an interactive demo. But for this, you will basically go through and like establish your search domain, what types of models you want to be using, what techniques you're going to be setting up, what your input data will be like, and where that data is going to be from. But not necessarily any of the actual data processing. It will only take the final like data set for that model. And then after you've established your search space for all of the models that you are going to be trying out, they allow you to either sequentially run them locally or distribute them across a different utility, depending on how it's set up. So you usually need to have something like Dask or Apache Spark or something else running in the background to do that kind of cluster management, to either process the individual like jobs that these things are going to be spinning out, as well as to feed in data from the other parts of your pipeline. So while the out of the box solutions may uh, have that automated all the way from the data step, these AutoML frameworks start after the data processing step, but before the actual model training. And then finally, we have the DIY solution, which you can do with like literally any language in any way. Obviously, it is the most extensible. What I'm going to outline here is that if you are familiar with like containerization or setting up containers, and if you're not familiar with that, and I don't expect you guys necessarily to be, that would be essentially what the normal operation procedure is for doing like these more sophisticated ML ops without having to rely on any specific external tooling, uh, by setting up just a set of operations that need to be run within a single container, and then like basically setting up your application, or setting up your each ML operation as an individual container that you can then organize and orchestrate together in a way that you can pass in the outputs of one container to the next one and be able to do each process in a way that's very like scalable. So uh, there's different tools for managing this, and this is actually what GCP does on the back end with Kubeflow as well. And actually, all of the out-of-the-box solutions secretly do this, in that whenever you define a function or something in SageMaker or ML pipelines, what it's doing is it's provisioning like some resources, putting it into a single runnable container, running the Python script or anything else that you've written in there, uh, feeding in the outputs, and then putting them out into the same location. And you can like uh, you can mirror the same usability with something like Argo running alongside of these things that will allow you to basically set up that in a very like in the same way as you would internally. So I'll take a quick break here. We have like 20 minutes left, which is a bit less time than I had anticipated. But uh, I'll just answer the one question we have, which is basically, are pipelines helpful when doing ad hoc work, or is it mainly for production? I think I've kind of answered this already. Uh, it is all right for doing an ad hoc work, provided the ad hoc work you're doing is something that is going to be extensible, right? So uh, basically, uh, basically, it's useful in the model exploration phase of training as well. And you don't necessarily have to only use it in production or optimizing of, or in the optimization step of training the model, simply because it does help you do this sort of search space reduction or search space exploration to help you minimize the amount of things that are there. So uh, that's the one question we had, and I am not sure if anybody else is going to ask anything. So I'll leave like a couple. I'll leave like 2 minutes for questions, and then we'll go into a quick demo of how to set up Teapot, as well as how to use like DAS to do some data transfer. All right. So here's just I have a couple of quick like examples about how to set up different sorts of operations here with Dask, and I can just go through a couple of these in short order. So basically, what we'll be setting up on the side is uh, you can basically take the existing solutions that you have for your Jupyter notebook and build out with a tool like Dask, essentially the cloud or cluster-based solution there directly to your application. So for that, as an example, let me open up this NYC taxi like system. So this is just the normal like Anaconda New York City taxi uh, output. So let's actually, I accidentally terminated uh, my Jupyter notebook earlier, and it didn't save the kernel. So I do need to go through and rerun it. So this might take a second longer than I wanted it to, but not super long. Let me just grab these. And right, so I'll just go through just the basic setup here while that is quickly running. So basically what we're going to be doing is we are going to set up like a standardized data frame across a cluster that can then be used by other jobs within a certain client, within a certain like task group. So from there, from there, basically what we're going to be setting up is we're going to be building out the overall New York City taxi input from the CSV, loading it directly into a pandas data frame, and then with that data frame, we're going to be storing it into this DAS cluster, and then persisting it across this instance to then be used in subsequent operations. So from that, basically this would represent the first step of your data pipeline operation. So to give, so as soon as this is done running, I can then set up the actual steps here. So let's do that. So the benefit of this is that you can basically read in and store any of this data for any length of time and just keep it ready to go for subsequent operations. And then once you have this set up, you'll be able to then call upon different components within the same cluster without having to necessarily individually run or individually manage specific like use case, specific data things. So this allows you to easily create different blocks that you can then feed across to different steps, feed back into the same cluster, and then go through and coordinate and set up basically that entire operation across the whole cluster and how it's set up and computed. So to give you a quick example about how to just run certain operations there, you'll be able to basically describe the direct explanation here for each one of these. This shouldn't take too long to run, or I mean, it's taking long to run because I am installing something right now. But when that's completed, make my screen larger. I think I can do that. How's this? All right. So basically, uh, what we've done here is essentially we've read in the raw data from the data set directly as you would do normally. So you would in the normal operation for setting up a Panda data frame, you would just read the data frame directly from the input source, and then you would do the rest of your operations with the data frame to do any of the parsing or processing of different items. So if you want to like find the max or median or do some additional feature engineering or do like a map reduce on certain ones of these to try and like discretize or try and like remove some additional components from here, you would just set that up in the data frame, and then you would produce your input-output columns, and then you would do your training and all those sorts. But because each one of these operations is something that can be both very time-consuming, especially as you're dealing with larger data sets, and also very useful for other operations within your application. Having to rerun this multiple times or having to just keep it out as a separate individual file that you then need to pass around is not the most sustainable solution in the long term. So this is part of what I was saying earlier about trying to think about things as more of not individual steps, but as modularized like the think of things more as modularized components as opposed to something that you're just sort of running for the purpose of like seeing the output of in in uh, in in a Jupyter notebook. So you can essentially run all of the same operations as before, and what we'll do is it'll automatically load in the data from there into the data frame itself. And from that, you'll basically be able to go through and build out each one of these directly. So it should automatically come in here and finish loading in the data in a little bit. Uh, but uh, this is something that would be scalable across multiple different setups here when it comes to establishing each one of these components directly. It should not take this long though, and I do think it's something that's wrong with my configuration. Unfortunately, I did set this up beforehand, but it seems like it didn't uh, stick around while I was having some other issues with signing into this. But yeah, my Python code and the slides, I can make them available. And we can also go through and specify the specific items here as well. We only have about 10 minutes left, and I'm not sure if I will have enough time to go through the whole demo. So I think what I'll be doing is just covering a couple of the more basic components here, as well as showing you some more of the examples that I had available in this round. So I also want to show you basically setting up things with Teapot as well. So basically, Teapot is a similar technique to automatically do different automated machine learning operations. So as I mentioned before, basically what you do when you define something with Teapot is you're going to go through and after you've established what your input data is, in this case, we're just going to be using the MNIST like digit data that's available from sklearn, and you'll just establish your search domain. So first split that out, and then secondarily define what your search space will look like. And actually, Teapot uses a genetic algorithm to automatically determine these conditions. So in order to define the search space, essentially what you're going to be doing is you're going to be determining how many different operations or how many different uh, like individual models you're going to be trying out, and then how you're going to be using that to basically optimize for particular criteria. In this case, it's going to be accuracy. So let me actually start off this one so I can use the same kernel for all of them. Then I'm going to reset everything here. And then basically pass on over the rest of this operation. And then basically passing over the rest of this operation from the other setup here and be able to run through it. Um, 1 second. Right. So, yeah, unfortunately, I have a little bit more technical difficulties than I wanted to during this presentation. But basically, we can go on into this next step here by just setting it up on the side. Let's get this running. Okay. All right. So it's relatively straightforward to set up from here. When you're setting up the generations for the classifier as it comes out of the box, basically what you're going to be doing is you're going to be establishing the overall generation and population size for each one of the iteration groups that you're going to be running, and all of the populations can be run simultaneously. So when you set up a cluster with Dask, what it will do is it will distribute out each one of these operations to each individual like CPU within your cluster, or each individual each individual machine within your cluster. And from there, you can basically immediately scale out and search a whole set of these. And the more you parallelize the situation, the more you can cover, and thus the more search areas that you cover, the faster you'll be able to basically find the local, find the true loss minimum, right? So you can definitely go through and set this up in a very straightforward way without a whole bunch of additional effort, provided you take the time to basically set up your system in a way that can easily built out to do that. Yeah, I also hate when my code crashes during a presentation, especially when you like set it up beforehand, you're like all ready to go, and then you have an issue. But yeah, so I can share this with you. In fact, actually, all of this is available within DAS example set as well. So uh, there is a lot of good documentation about it. I will, I guess, hang around for a couple minutes afterwards and just share the documentation for some of these, as well as the location for specific items, and my presentation as well. So you can just take a look at that in your own time. Outside of that, I can't necessarily uh, like show the rest of the stuff within the next 4 minutes or so, because I will need to rerun it again. But we can just do a little bit of Q&A here, in case you have any like specific questions. All right, so for some reason the model's not showing the nice output it usually has, but it normally generates things like this, where you can just see the each individual step for each generation. So for each one of these, basically it's trying to pick the best one out of the CV scores based off the parameters that you're optimizing for. You can actually specify within Teapot which parameters of the model you want to cover. For the models that come as built-ins, this is easily like doable. But for the models that you may want to add in from other like systems or sklearn, you'll need to go through and essentially create a wrapper class essentially that will be able to allow it to dynamically make the adjustments for each one of these. So basically, as it works like most genetic algorithms work, where you'll just select from the top set of performers from a certain generation, and then create variants of the subsequent generations based off that performance. And then from there, essentially, it will then be able to optimize the model based off of uh, which ones of these are most relevant, and then be able to give you an overall like external CP. So you can then, in order to improve the efficacy of how much ground you're covering, you would both increase the number of the population size essentially, and then you can also increase the amount of depth that you get, at least in terms of how far down you are going to be parameterizing after you've established this by going through and setting up the number of generations. And then by doing that, you can sort of get the best of both worlds when it comes to doing the random selection for sampling when you're doing optimization, both in terms of the overall model itself as well as the technique. Uh, by being able to sample a wide area and get a good lay of the land, as well as to be able to more specifically hone in on specific gradients, similar to how Bayesian optimization works, without necessarily having to rely on doing it in an exclusively sequential way, which can drastically reduce the amount of things that are set up. All right. Well, thank you all for coming by. Sorry about the technical difficulties at the end. I'll stick around for a couple minutes after the presentation to send some of the results, not the results, to send some of the documentation out, and I hope you guys have a good day.